Looking at number 7, if you're doing a hypothesis test about a proportion, one sample with summary. And so this sample said that we sampled 150 people and there was 125 successes. I'll just say we did 200 people and had 125 successes just to mix up the numbers a little. And then you go down and enter what you think the proportion should be. What your null hypothesis is that we have 90% successes in our population. And we're testing if it's going to actually be, in fact, less than that as our alternative hypothesis. And if you look at our sample, if 90% out of 200 would be 180. So if our population really had 90% successes, and then we took a sample, we would expect out of 200 to have about 180 successes. And so this sample is way less than 90%. And so there's always those rare samples that produce something like that, but there's also the chance that the reason our sample is so much under 90% is because the proportion really isn't 90%. It's actually less than that for the population, and we need to reject our null hypothesis. So that's the whole idea behind the hypothesis test. I entered in my data backwards here. We had 125 successes out of the 200 total we sampled. And so we're doing our hypothesis test. The probability of getting a sample as rare as we did, if this is true, if 90% is true, the probability of getting our sample is told right here in our p-value. It's less than 0.001. So out of 1,000 samples, it is going to happen one time out of 1,000. But that's really, really rare. What are the chances that we got that sample? So, based on that being so rare, it's more likely that this null hypothesis is just incorrect and we should reject it in favor of the alternative hypothesis. But yeah, there's your p-value, there's your test statistic. Excuse me, your test statistic. StatCrunch shows it to you right there once you hit compute. You also sent me a question about number 12, and it looks like you got the values right. I'll talk a little bit about D, but I don't know if you still have questions. Good job getting all these right. Your test statistic is in between these two values. You got your negative value down here, and by symmetry it's the same numbers, but the positive version up here. In any test statistic that's in between those, we're not going to reject the null hypothesis because it's plausible. If this is the true mean, that anything in the white, that's a realistic test statistic for us to get back when we run a sample. We only think there's sufficient evidence to reject the null hypothesis if our test statistic is way out here in the tails. Sure, it could happen in a very rare case, a very rare sample. You will get a sample that's out here in the tails, but the more plausible explanation is that your mean is just wrong. Your mean is something different in the middle here. Maybe it's way farther to the right, and that's why you get a sample that's way farther to the right. So that's why we reject the null hypothesis when we're out here in the tails. But from what you got, this test statistic is in between. It's in that white part close to the mean, so there's not sufficient evidence to reject it. To reject the null hypothesis, since the test statistic is between the critical values there, in between, close to the mean.